Hello students, we were discussing the direct sequence per spectrum communication systems. In continuation of that, today we will discuss the performance analysis of this DSSS system. Hope you will remember in the last module we discussed about the receiver architecture. Two different kind of the receiver architecture we have discussed. The last one was match filter based receiver, and where the demodulator circuit was a correlator based. And this is the same figure that reproduced here in this module from the last module, where the chip matched filter is basically matched with the chip waveform psi t, hence its impulse function, its transfer function will be is equal to the psi of minus t, if psi t is my chip waveform. RT signifies the incoming signal that is entering into the receiver front end, and this is the synchronization device who is helping basically to sync the incoming signal with the receiver circuitry, and it is also bringing down the received signal from the RF to the baseband. The matched filter is basically selecting and then maximizing the selecting the signal and maximizing the signal to noise ratio at the output of this filter, provided the input signal is properly synced. And output of the matched filter will be now be sampled at the rate of the chip duration Tc to provide the capital G number of the samples. Why? Because we saw in the transmitter that G was the processing gain, and basically G was telling about the number of the chips available over the symbol duration, and G was given by Ts by Tc. And once actually the sampler is sampling the G number of it is producing the G number of the samples, and if the chip clock rate is properly synchronized, it is properly synchronizing the sampler with the spreading sequence generator. Spreading sequence is now helping you to despread the demodulated sequence, and Zi represents the output of this despread signal. The accumulator here is now accumulating the number of the samples, it is accumulating the number G number of the samples that you have obtained over a symbol duration of Ts, and decision device is finally taking the decision about the demodulated signal to identify what was the message information transmitted from the transmitter. We will revisit on the waveform part of the transmitted signal, as well as we will try to look into the detailed mathematical expression of all the points of this Zi, V, and we will try to identify finally how this whole system is working. Today the work is the mathematical analysis of this whole receiver architecture to have a detailed knowledge of this receiving process. Remember this RT when we were receiving at the front end of the receiver, that RT is now the combination of the intended signal transmitted. This is the spread signal which is transmitted. ST is the combination of our XT into PT, where PT was our spreading waveform and XT was the modulated signal, and XT was and IT was the now jamming signal or interfering signal that is getting added with the transmitted signal on air. NT signifies the additive white Gaussian noise, and this is coming from the thermal noise component of the transmitter receiver front end circuitry. So, the system model with which we will start our analysis will look like this: the ST, the intended signal, intended spread signal in presence of the jamming signal and the additive noise we are receiving. We will come back to this receiver block architecture whenever will be required in the subsequent slides. So, this is a recap of the transmitted waveform, generated waveform, and the spreading and the dispreading process. In the transmitter, we took the signal dt like this. Remember, I have utilized for the 0 transmitted signal as plus 1, and transmitted signal 1 will be is denoted here as minus 1. PT and the transmitted signal had the signal duration, symbol duration of Ts, and locally generated PN sequence bit stream was having a duration of chip duration of Tc. The chip waveform is governed by the figure number D, and the spread signal was generated by the XOR operation of these two. And as we understand that in the XOR operation, when the data signal value was 0, he was allowing the XOR operation will allow all the PN sequence chip, and if the data value is equal to 1, he will invert all the PN sequence chip. So, if you go by that logic, and you will be able to regenerate this spread signal. So, this is my DT, this is my PT, and this is the ST, the spread signal of transmitted from the transmitter. This is a time diagram. If we look, this is a time axis based on which you are getting. If I look into the frequency axis, so we after the spread signal, we have got the spread waveform. This is my signal now ST with the spread spectrum signal, where the signal bandwidth is now coming W, as we discussed earlier. And the interference now that is getting added on air, we are considering it is a narrow band signal who is having some bandwidth is equal to B. So, this is the way now the relative spectrum of the signal as well as the interference with which we will be dealing with in the receiver. In the receiver, after receiving the signal, this signal ST here, which is now basically coming to us as RT, where RT is equal to not only ST plus my interfering signal IT getting added to it, as I have seen, and with that actually the noise signal is also added, that is shown in the previous figure in the block diagram. So, let us consider that NT is negligible. So, basically you are receiving ST plus IT, and which is shown here as the received signal. You have a locally generated PN sequence bit, because you have a prior knowledge of the sequence with which you have spread in the transmitter, and once you are regenerating that signal, and if we consider that they are exactly time synchronized, so we can by another XOR operation in the receiver, we can reconstruct our transmitted signal DT. So, final diagram here is a reconstructed signal and then as well as a disparate signal dt recovered from the received spread signal C in presence of the interfering signal. If we try to see then, as this is again the time axis interpretation, if we try to see on the frequency axis, so after multiplication of the received signal with my spread signal PT, we will because actually the dispreading operation, the signal will come back, the signal bandwidth will again will be compressed to the original bandwidth B, and now as the interfering signal was not spread earlier, it was newly added on the air, and now because of this and this demodulated dispreading operation uniformly is operated both on the ST as well as IT. Now, IT multiplied with PT will expand the bandwidth of this IT, and hence the bandwidth of the interference now will be spread over the bandwidth of the PT, which is now W. And going by the gain bandwidth product constant, whenever my bandwidth is expanding, the power of that corresponding signal is coming down. So, now you can see that the technique gives an inherent resilience with respect to the interference, because power level of the disparate signal in the receiver is much higher than the maximum power level of the interference. So, this is the margin over which your signal is, your receiver is operating. your signal SNR, signal power, is this much higher compared to the noise power or the interference power. So, it will, based on that you will have to detect your signal. So, this is the fundamental of the transmitter receiver architecture of a direct sequence spread spectrum system that we discussed in the last module. Here we have recapped it. From now onwards, if this is the was the concept, and if we look back the block diagram which was there in the first slide, we will be seeing that the demodulated sequence, as I have explained there, the demodulated sequence in the receiver generated spreading sequence, they are multiplying, getting multiplied together, and these successive such products. So, then we are adding up and considering that there is a perfect synchronization getting maintained. And remember the effective sampling rate of the decision device, now it will be the symbol rate. So, there is a change in the sampling concept in this receiver. Remember the sampling here you are doing is at the rate of the chip, because that is the way the timing diagram is of the received signal, timing information is in the received signal. But once you have actually added all the samples, so you will be ending up with, after the accumulated, you will have the time donation which is over the notation which is over the symbol duration Ts. So, decision device will be working on the symbol duration, whereas the initial sampler will be working over the chip duration. And so, that was the case, and we understand that all the sequence generator, the multiplier, the summer function, they all can be implemented as a discrete time filter and match to the spreading sequence. Remember one thing, this match filter implementation won't be practical for a very long periodics, very long kind of the spreading sequence, because that will be extending over the multiple number of the data, very large number of the data symbols. If that is the situation, then match filter implementation is not practical. However, we will come back to the mathematical model. We started with RT is equal to ST plus IT plus NT, which we now understand this integrated model that we are receiving at the front end of the receiver. We have modeled NT as additive wide Gaussian noise, that is mentioned already. The ST was a form of my A dt pt cos 2 pi fct plus theta. We understand now fc is the transmission frequency, theta is the random phase associated with it, dt is the modulated signal, and pt is the spreading waveform. All that part we have also currently seen in the timing diagram as well as in the frequency diagram, what will be the spectrum of ST after this operation. Remember this equation 1.1 holds good if actually your delay tau is autocorrelation delay, the tau is exactly integer multiple of your if it is integer multiple of the Tc, that chip duration Tc. If it is not that, actually the tau is greater than, actually it is not an integer multiple, it is Tc plus some epsa, if tau is something like that, that we have already seen in the first module. If it is Tc plus epsa, then the transmitted signal module will look like this. We have discussed it earlier. And if we assume that this theta value is equal to 0, so there is no phase uncertainty inside the received signal, so we can omit the presence of theta in the received signal. And moreover, if the chip waveform psi t with the duration is Tc in the received signal is present, and which will be modeled later on as a rectangular waveform, we will come down to the equation 1.3 where theta is not present. See, this A is now replaced with square root of 2s. S is the average power of the received signal, and rest part we have already, so the symbols we have already discussed. Now, this each pulse dt, it is having a data duration of Ts, that already we know. The spreading waveform Pt is given by this that we have seen already, which is an infinite sequence coming, and psi t is a waveform. Pi can be either equiprobable to get either +1 value or -1 value, and hence actually it is a part every Pi, the sum of all the Pi's is constituting the spreading sequence. Without any loss of generality of this discussion, we can consider that this chip waveform is having a normalized to unit energy, such that if we integrate it over a TC and normalize it over the duration of the chip, I will get the total energy equal to 1. And this transition of the symbols that we have discussed, that this transition of the symbol and the transition of the chips, they are coinciding actually exactly in the same timing duration. That means they are in the sync for our discussion. The processing gain will be given for the spread spectrum communication is Ts by Tc. So, with all that consideration, let us start with the understanding that we have transmitted the dt is equal to d0. Let us think that the whole explanation will be continued now for the data value dt transmitted is equal to d0 over the time of interest. Then remember that Zi is the location, Zi is the data symbol that is coming after the demodulated sequence getting correspondingly multiplied by locally generated PN sequence. This is here. So, we have considered the RT, then we have thought inside the ST the condition of the dt is equal to d0 over the 0 to 2s. We have sampled it, we have multiplied with locally generated sequence, and then we are here inside Zi. So, Zi, the equation of Zi we can rewrite as this. We receive the signal RT. Now, the locally generated PN sequence is multiplied with it, and it has a cos 2 pi FCT multiplication, because you are having the cos 2 pi FCT synchronization at the front end, and the integration is we are interested to first chalk out the received signal over a chip duration, a single chip duration. And remember, whenever you are running such kind of integration, after Zi there is a accumulator. So, you are bound to derive the Zi's which were over 0 to g minus 1 number of the samples. If I look inside this, zoom inside this RT, I understand it has 3 components: the intended signal component, the jamming component, and the noise component. Whereas the signal component is given by the ST. So, each of these components will be now investigated separately. The value ST will be multiplied with the locally generated PN sequence. It will generate the sample SI, and this is the expression for the SI. Similarly, the jamming part, when will be multiplied with the local component PN sequence component, it will generate the sample value of the Ji. And similarly, the Ni for the noise part also, we will get the NT getting multiplied with the spreading sequence, and then we are ending up with the value Ni. Good part is, if I see inside this Si, you see that this ST is now will be substituted by the summation of this Pi and the D0. And remember, as we are interested only over the ith chip, there is no summation coming up over all the Pi's. So, it is only just a Pi and multiplied with the value of the data who is considered to be here D0, and there is a summation, because we considered here to be the S2S is the total amplitude of this signal, and that is coming out, and there is a portion left inside the integration, which is a cos 2 pi FCT dt, that is getting multiplied with psi t. Remember, inside your ST also you are this psi t is basically inside ST also there is a component of the psi t, and this 2 psi t will be multiplied and will be generating psi squared t minus ITC, and we have considered that it is having unit energy. In the last slide we have seen. So, you will not get any component left for the waveform side, you will be left with cos square 2 pi FCT, and this integration cos square 2 pi FCT if I am considering width, then and again considering that this f c is is really too high compared to 1 by T c, then the higher component, the second order or the higher component value of the cost won't be good enough to contribute anything inside the component of the SI. We will neglect all those terms. So, we will be ending up here with the cos square 2 pi f c t, where by adjusting the 2 here, we will get inside the 2 cos square 2 pi f c t. We will be further by trigonometric identity can be boils down to 1 plus cos 2 theta. And that cos 2 theta term we are neglecting because of this logic, and hence you will be ending up only with the integration of I T c to I plus 1 T c dt, and who will bring you down to the computation of to the value of T c. Finally, with all this logic, we will be ending up with P I d 0 s by 2 into d c in the intended signal component. We are interested to see what is there left, how the component Z I and N I will be computed next. Remember the input to the decision device. Decision device input is now having 3 component again, like Z I. He is having the component from the intended signal that we have already calculated at d 0 square root of s by 2 into T s. Because now it is becoming T s, because you are having a addition over the G number of the sample. So, you will be ending up after accumulator, you will be ending up over the sample symbol duration. There is no chip duration concept left, and there are the components from the jammer and jamming signal as well as from the noise signal. From the jamming signal, although J part all the JIs are getting added over, and this Pi into Ji, that is the section you are left with, all the Pi's where with their corresponding Ji's are getting multiplied and added over. Now, remember one thing, that suppose that d 0 is equal to plus 1 represents the logic symbol 1 and d 0 equal to minus 1 represents the logic symbol 0. Then the way decision device works is, if the symbol value is 1, then the decision device will give you 0 greater than 0, and will give that, will tell that symbol is equal to 1 if the value of this capital V is greater than 0. So, if value of the V input to the decision device is greater than 0, the decision will be that the transmitted symbol was 1, and if the decision device input value V is less than 0, then the decision device will tell that the transmitted signal was transmitted as minus 1, basically it is 0. So, if this is the situation, then there is no chance that V can be exactly equal to 0. So, V value will be either greater than 0 or V value will be less than 0, because we have modeled the transmitted signal as either plus 1 or minus 1. So, probability of getting V equal to 0 of no chance. And when error occurs in a situation when if V is less than equal to 0, when transmitted value was actually plus 1, and V is greater than 0 when transmitted value d 0 was exactly minus 1. So, whatever you transmitted, but because of the some problem inside the, because of the high impairments from the jammer as well as from the noise components, if it brings down the value of the V in such a way that it goes below 0 when actual data was transmitted 1, then you will get an error in the decision process. The white Gaussian noise that we have considered. So, we have to now think little bit about the variance part, the variance as well as the mean value of the V we are interested in, because that is the part we understood that there is a randomness in the jamming plus the noise section, who will actually greatly interfere in the decision process itself. So, we have to understand, as it is a random process, both the jamming plus noise, it is a random process. So, its statistical property, second order statistical property, that means the variance will be a very important part for our consideration, and which will from where actually we will take care of the fact that how much error probability we are expected to get in such kind of the scenario. To start with, we will think that we will see inside the white Gaussian noise process, as it is a Gaussian noise, it will have the autocorrelation function given by this classical expression, and we understand this n 0 by 2 is a two-sided power spectral density of the noise, and eta 0 by, as it is a white Gaussian noise and it has a mean value is equal to 0. So, we see that the expected value of the V 2 is equal to 0, and so the straightforward calculation we will be ending up with to compute the variance of this guy. How? By if we substitute the value of n I into my V 2 and then try to compute the square of it to compute the variance, where this squaring of this n I basically will end up with the squaring of this n t, which is nothing but the autocorrelation of n t with itself, where we can substitute the value of this autocorrelation function, and taking care of the fact that psi t, if psi t is equal to rectangular function to us, and we will be ending up with the variance computed as 1 by 4 n 0 into T s. Why this T s? Because we are at the input of the decision device, where your psi t will, the P t inside will be substituted by the addition of all the points over 0 to g, capital number of capital G, all the number of the sample points, and this n 0 by 2 is the contribution from the autocorrelation function. Another half is coming from the fact that we have to take a 2 cos square theta inside the integration, and the higher order terms again will be neglected, and that half will come as a additional part multiplied with this n 0 by 2, leading to the 1 by 4 n 0. T s is coming because there is a addition over the accumulator over the number of the samples equal to capital G. And see, it is desirable that this we will try to do the modeling over the long spreading sequence as a random binary sequence, and this random binary sequence model doesn't seems to obscure the important exploitable characteristics of the long sequence, and it is reasonable approximation even for the short sequence also in the networks with this asynchronous communication. And then with this hold good, this computation of this V 2, its variation, its variance, there is no effect of this, because they are the jammers and the noise, they are the completely independent and identically distributed two quantities we are dealing with. Now, we have to look inside the another part left, where actually V 1 is there. V 1 is the jamming section, but in order to understand the jamming contribution, the power contributed from the jamming section, we have to understand that the jamming is not now alone standing here. In the receiver, the jamming, the jamming signal is already got spread by the spreading sequence P t. So, its whole spectrum, its spectrum is getting dominated by the spreading signal. The property of this P t now we have to look into. We understand that this random binary, if we utilize the random binary sequence, then it has a statistical property we have already discussed, that this will have a statistical property such that it can take a +1 value or -1 value with equal probability is equal to half. Thus, your mean value of this P I is which is equal to also P t, it will be equal to 0. And then we come to the value that if the mean value is equal to 0, and then the mean value of V 1 and mean value of V 2 in V, we had a component from the signal, then the value V 1 and V 2. We already seen that the mean value of the V 2 is equal to 0. Now, we have proved that if you use a random binary sequence, it will lead the mean value of V 1 is also 0. So, both are equal to 0. So, the mean value of V you will be ending up with is the expression d 0 square root of s by 2 T s. Now, if I look into the variance computation, as I and j are independent to each other, because each and every random because of the randomness involved in this binary sequence, in the PN sequence, your ith and jth component of that sequence, they are independent to each other, and hence we can actually also see that pi into pj, that mean value, mean to pi and pj, that will be also 0, and the variance will be straightforward computed by the individual component ji square or summed over g number of the samples. So, finally, the variance of the V will be sum of the variance you are computing here plus the variance of the noise that you have we have computed in the earlier slide here. So, they are the two variances that will be finally important for us to compute the signal to interference noise power for the decision device, which will largely actually control the decision of the decision device. We will see in the next module how actually these powers, corresponding powers, are playing the role in the decision device. Before ending this talk, we would like to highlight little bit and reframe our understanding of the processing gain that we are continuously talking about in the direct sequence spread spectrum system. Remember that this processing gain was declared as the ratio between the transmitted symbol duration by the chip duration, which is also given by the spread signal bandwidth W by the original signal bandwidth B, where W was 1 by the chip duration and the signal bandwidth was 1 by the symbol duration. Usually, we express this processing gain in terms of the decibels or dB. This processing gain ratio, I mean this dB value, is fundamentally, it tells that by which amount the unwanted signals or the interference signals can be suppressed relative to the signal itself. So, if this factor, always this factor will have some integer value. So, and that factor, the value that you are computing here, directly tells by this amount the interference can be suppressed with respect to the signal when both of them will share the same frequency channel and the same frequency channel for the transmission. And remember, this processing gain has no effect on the wideband thermal noise. So, the jamming process, as I was mentioning in the earlier slide, the jamming process and the noise process, they are completely independent and completely independent to each other. For example, here is a short example is given here for your understanding. If I am having a 1 kilohertz signal and I spread it to 100 kilohertz, then the simple processing gain will be equal to 100, or in the terms of the decibel it is 20 dB. So, its computation of this processing gain has no effect, is never actually getting influenced by the computation of any noise power.